In this video, we're going to talk about how to tell where functions are increasing and decreasing by looking at their derivatives. What I mean by increasing is that we're going to be able to tell where a function is going up and to the right, and decreasing means going down and to the right. So for example, this function here would be increasing from here to here. Right? We would say it's increasing there, and then it's decreasing from here to here, and then it's increasing from here thereafter. Now, we need to know how we're going to be able to tell what a function is doing roughly just by giving its equation, f of x equals whatever. And there are four possibilities for telling what could go on here by using the derivative. I'll say if f prime is if the first derivative is positive on some interval, then that implies that f is increasing on that interval. So that's what we use to tell. And if f prime is negative, that implies that the original function is decreasing on that interval. And the other possibilities are if f prime equals 0, what's happening there? Well, if f prime is equal to 0 on an interval, it means that it's flat, it's constant. But typically this only happens at single points, right? Like, for example, in this case here, the derivative is 0. The derivative of this function is 0 there, and it's 0 there. So we have horizontal tangents. So it's constant, I guess we would say, just at this one single point. But usually when the derivative equals 0, you'll have one of four cases. It's just going to flatten out. It will have something like this, or it could be like this, right? Horizontal tangents. Or it could be a dip, flattens out, or it could be a hump like that. And the other case is where f prime does not exist. If the derivative of a function does not exist, then that means that the original function could have a corner, right? It could have a vertical tangent at the point, or it could be discontinuous somehow. It could be like this. It could be an open, continue on, or it could be an asymptote at that point. A variety of things could be happening. Mainly, we're going to be concentrating on these first two cases. We're going to be given functions, and then we're going to take the first derivative and see where it's positive and negative, and based on this, draw conclusions about what the original graph could look like. So these are the four basic rules. This is all that you really need to know for now. And so we know what increasing and decreasing means. So let's do a couple of examples. Alright, the first one I have is the parabola. The question, I have four problems here. The question for all four is going to be determine where these functions are increasing and where the functions are decreasing. So the standard method for doing this is to take the derivative and examine it. So in this case, f prime is 2x minus 2. And basically we want to solve this. We want to know where is this positive, where is this negative. The way that we do that is whenever we take a derivative, we factor it as much as possible. So 2x minus 1. And then typically we wind up making a sign chart for this. So I'll draw out my number line here. And we see that this expression is going to it all kind of revolves around where the derivative is 0. So in this case, the derivative, I say at an x value of 1, the derivative is 0. And if you plug in a number greater than 1, the expression will be positive, so I fill in a plus here. And if the derivative is, if x is less than 1, then the derivative is going to be negative. And this is all the work that you need. All right. From this, we conclude that the original function, f of x, it's decreasing from minus infinity up until 1, where it has a horizontal tangent. And then after that, it's increasing because the derivative is negative and then switches over to positive. And it's just that easy. Now we know what this function looks like because it's just a parabola. It's basically going to look something like this. Alright, they all sort of do that. So this x value here would be equal to 1. I don't know what it looks like exactly, but I can be sure that at this point x is 1, increasing after 1, decreasing prior to 1. Now let's take a second example here. Minus x e to the minus x, a little more complicated. I'll save you the work. If you just do the derivative, g prime of x equals, once you do the product rule and you work this out and you factor it completely, what you'll get is minus e to the minus x times the quantity 1 minus x. If you want, you could factor this negative inside and you could get e to the minus x. Why don't I do that? X minus 1. So this is it. You do the same thing that you did in the last problem. We're going to make up a sign chart. Alright, you mark down where is the derivative equal to 0, so it's clearly at 1. The derivative is 0. If we plug in a value of x that's larger than 1, this term will be positive, and the exponential is always positive, so we'll get positive on this side. And if you plug in a value of x less than 1, this term will be negative, and this is always positive, so we'll get a negative over here. And from this we can tell that since the derivative is negative over here and positive over here, that the original function x e to the minus x must be decreasing up until 1 and then increasing thereafter. Now, the reason that I give you these two examples specifically is notice that this and this, so these two functions, this function, which is the predictable parabola, and if I can fit them both in on the same shot here, and this thing, which is definitely not a parabola at all, they both have, their derivatives both have the same sign chart. So they're both decreasing and increasing on the same intervals. The reason I bring this up is that to illustrate that you get really very little information from just doing a sign chart for the derivative of some function. Right? All that we can tell from this is that the function is decreasing and then it's increasing. If I had taken this out of, so if I give you a function, if I say that this is the sign chart for the derivative of some unspecified function, you really don't have any idea what it could look like, right? All that you can tell is that it's decreasing here and then increasing here, and that could mean a lot of things. You could have, let's say I have, I'll just make up a function that has these properties here. All right, if this is 1, it could look like anything. It could look like this. All right. That's one way, right? It's decreasing and then it's increasing. It could look something like, it could look like a parabola. It could look something like, it could be decreasing like this linearly and then go 0 and then come up and have an asymptote or something, right? Grow really slow. So there are a lot of possibilities here. This is only supposed to provide us with just the basics about what the function is doing. Just increase and decrease. But this is how it's done. So I have a couple more examples. They all kind of go the same way. Same instructions here. We have y. Let me just adjust this. And the question will be, tell me where this function is increasing, tell me where it's decreasing. So you take the derivative. Alright, so x cubed, you get 6x squared plus 5. That's it. And so you draw out your number line. Make a sign chart for y prime. And notice it doesn't have any zeros. In fact, this expression is always positive, right? Because 6 times something squared plus 5 has to be a number that's at least 5. So if I do a sign chart for this, I just write a big plus sign. So because the derivative is always positive, we infer that the original function must always be increasing. So an increasing cubic, we don't know what it's going to look like. We could graph it to figure it out. That's not the purpose of this, but it's since it's cubic and the end behavior says that it falls left and rises right, it's probably going to look something like this. All right, something that's always on the increase. It never flattens out. It never comes back down. It's always an increasing function. But this is what it looks like. And that's it. That's all we get from doing the first derivative. And as a second example, tan inverse x, where is it increasing, where is it decreasing? So you take a derivative. Y prime equals, and the derivative of tan inverse is 1 over 1 plus x squared. And again, we realize when we go to plot this thing out that it's always increasing. Right? Well, I mean, this expression is always positive. It doesn't have any zeros, and it's never undefined anywhere because, again, we have the 1 plus squared on the bottom. So this is also always in this function is always positive, which says that the original is always increasing. Now this function doesn't look like this at all. Just to mention again that you really don't get a lot of information about what these things look like, just whether they're increasing or decreasing. The inverse tan function happens to look something like this. It has asymptotes at minus infinity and infinity, and it looks something like this. It grows kind of slow and does that. So, just having a plus sign for the first derivative doesn't tell you a whole lot, right? I mean, this is an increasing function, and this is an increasing function. So we're keeping it really basic here with the conclusions that we're going to draw from these sign charts here. Now, these aren't very complicated examples. I just did them to show you, just to illustrate the idea of how to determine where a function is increasing and decreasing. I do have another, a little more complicated of an example though, and that's right here. So we have this rational function. We want to know where is it increasing, where is it decreasing. So again, you take the first derivative, f prime, and I'll save you the work, but it happens to be x squared minus 2x over x minus 1 quantity squared. And so once again, we want to factor that. So we can make up a sign chart for it. So when you do this, you'll get, you factor the x, you'll get x minus 2 over x minus 1 quantity squared. So draw out your number line. Let's see how this goes. You want to mark down the numbers, the values of x that make it 0 and make it undefined, because those are the potential points for sign changes. So I say at x equals 0, the function is 0, and at x equals 2, the derivative is 0, and at x equals 1, alright, at x is 1, it happens to be undefined. So to mark that down, I just write an x there to let us know that the function does not exist there. Then fill out the rest of the sign chart. So if I plug in a number greater than 2, every term is positive, and I get positive over here. If I plug in a number between 1 and 2, I could test it out, I'll get negative. And if I plug in a number between 0 and 1, I could put it in and work it out, I will still get negative. And then if I go to a number that's less than 0, the whole thing will be positive again. So what we get out of this is, just from looking at the chart for f prime, the original function must be increasing up until 0, and then decreasing from 0 to 1. Then it's undefined because in this case the function has a vertical asymptote, so that's a discontinuity. So it's decreasing, undefined, then it's decreasing again between 1 and 2, and then finally after that it is increasing again. Now, we don't really know what this function looks like, but it's not that important at this point. We only want to know where is it increasing and decreasing, and this is how it's done. Now, there are other versions of these problems where you may be asked where a function is increasing and where is it decreasing, but you won't be given a function to work with. You'll only be given, say, the graph of the derivative. One such example is like this. Typically what they'll say is, they'll have a set of axes here, and they'll say the problem will be, this is the graph of f prime. So they give you the derivative, and it might look something like, say, this. Suppose it looks like that. And they're going to want to know, where is f increasing and where is f decreasing? So again, they give you f prime and they ask you to make conclusions about the function f which is not shown. But the same principle applies. We know that wherever f prime is positive, f is going to be increasing, and wherever f prime is negative, f is going to be decreasing. So all that you have to do is just look at the graph and see where f prime is positive and where it's negative. So we say it's 0 here and f prime is 0 here, and so clearly in this region here f prime is positive because it's above the x-axis. Don't pay attention to the fact that it's decreasing, okay? That it's decreasing doesn't make any difference here. We're only out to figure out whether the original function is going up or down. So all that matters here is the sign of f prime. In fact, we can make a sign chart that goes along with this here. Right? At this x value, f prime is 0, and at this x value, again, f prime is 0. It's positive over here, negative in between, and positive thereafter. So to answer the question, given a graph of f prime, all that you have to do is look to see where it's positive and where it's negative, and from that you can conclude that the original function f, without knowing specifically what it looks like, we know that it's increasing up until this number, and then it's decreasing between this number and this number, whatever that is, and then it's increasing after this number. Later on, when we get better at this, we'll be able to determine the shape of functions with a little more specificity. For example, increasing could mean this, or increasing could mean this, right? For a function, if we say that a function is merely increasing, there's no telling whether it looks like whether it's got that shape, or whether it has this shape, or whether it's a straight line, right? All that we know is that it's going up. In this case, the rate of increase is constant. In this case, the rate of increase is decreasing, right? Because it's increasing faster here, so the tangent lines are steeper here, or are more positive here than they are at the other end. And in this case, the function is increasing at an increasing rate, all right? Because the slopes of the tangent lines are increasing. And then later on, we'll be similarly with decreasing. Decreasing could mean this. Decreasing could mean this, or decreasing could mean this. And we'll be able to figure out which one of these it is, right? Such a function here is decreasing, but the rate of decrease is actually slowing down, all right? Because the function is going from changing rapidly to changing less rapidly. Or we could have a function that's like this, that's decreasing so fast and then decreasing more quickly, or we could have a function decreasing at a constant rate. But right now, all that we really know from just doing the first derivative and looking at the signs, all we know how to conclude is that if f prime is positive, the original function must be shaped like one of these on those intervals, and if f prime is negative, the original function must be shaped like one of these.